5 and events. So what do you do? How do you find the probability of event A and B occurring? And there's two possibilities. The events might be independent of each other, or one event happening might affect the probability of the next event. For example, if you take a card out of a deck and you don't replace it, then the probability may change the next time. So we'll start with independent events. That's the easiest one. That means that the probability of one does not affect the other, and you simply multiply. What did we do with OR events last time? We added. Do you see why? What do you think happens when you multiply two fractions together that are between 0 and 1? We know probability always has to be between 0 and 1. Right? So what happens? Does it get bigger or smaller? It actually gets smaller because when you multiply two fractions together. Do you see why that would make sense to help you remember the formula? Because now you have two things that need to be true, that and that, so the probability of it happening is smaller. So think about that. So multiplying the result becomes smaller. Whereas with OR we added and it became bigger. So that hopefully that'll help you remember the formula that you multiply when you want and. So let's look at some examples here. Okay, in a survey at a HHS football game, 50 out of 75 male students and 40 out of 50 female students said they would prefer a new school mascot. If one male and one female fan are randomly selected, what is the probability that both of them favor the new mascot? So it's smaller than just one of them. We want both of them. So A and B. So let's start with what's the probability that the male student prefers a new mascot? Exactly, 50 out of 75. And what's the probability that the female student does? So you do times 40 out of 50. Now if it had been one or the other, you would have added, right? So the probability would be larger. But when it's and, you're multiplying, so you would leave it as, well, we can do some cross-canceling here, right? Because we're multiplying two fractions together, 50 and 50. 50 divided by 50 is 1, so those cancel. And you have 40 over 75. You can leave it like that, but if we want to get a better sense of what probability means, it's actually more helpful to look at the decimal. So if on your calculator you divide that, do you see how about 53% chance of something happening is more meaningful than 40 over 75? You know, because we all know that's larger than a half. Larger than half. So there's about a 53% chance of that happening. Okay, let's try another one. A survey found that 14% of parents allow their kids to stay out as late as they want on Saturday nights. If 3 parents are selected at random, what's the probability that all 3 let their kids stay out late? So do you see how it's like saying, it's kind of like 3 events, the probability of A and B and C. But it still works the same. You still simply multiply. So what's the probability that one parent lets their kids stay out late? Yeah, you can write it as 14 out of 100. For this one, I'm gonna just put 14% because that's the same thing as 14 over 100. Probability gives you great practice with fractions and decimals and percents. So and then does one event affect the other? So if one parent does, are they like talking to the other parent and trying to convince them to also? we hope so, but in this problem, are they? They're not, right? So that's why both of these are independent. So you simply multiply. So what's the probability the next parent lets their students stay out? It's the same thing. And what's the probability the third parent selected at random? It's the same thing. So you could also write that, of course, as 0.14 raised to the third power. Is a good use for exponents to write things more concisely. And so if you did that on your calculator, you would get this decimal. And so can you tell me what percent that is? This is great practice. 0.3%. Okay, to go from a decimal to a percent, you multiply by 100, always. So that would be moving the decimal to the right 2 places. So it would be a 0.3% chance that all three, there's only a 14% chance that one of them, but the chance, since it's so small, the chance that all three of them, it gets lower each time. So you end up with only a 0.3% chance that that would happen. So you kind of also want to make sure your answer makes sense. So let's go on to, we'll do the rest of this page together. So now it gets a little bit trickier when events are dependent. Okay, so this is called conditional probability because the probability of one affects the other. And this, let me write what this notation, please add it. So if 2 events are dependent, then the probability of A and B occurring is the probability of A times the probability of B. So probability of B given that little symbol, that bar, means given that A occurred previously. So this means the probability of B given that A occurred, and we like to write things concisely, so you just do B and there's a vertical line given that A occurred. And since A affects B, it changes. It's not just independent. So let's try it. So here is just, there's 200 registered college students. What's the probability that a randomly selected student is female? So what would the fraction be there? So here's your table. So when you have a table, what I like to do is add up the rows and columns. So how many total female students are there? Good, 120. So let's write that there so we see that. And then how many male students are there? 80, good. So how many total students do we have? 200, good. And then if we add going down, that should also add to 200 going across. So how many part-time students? Yeah, 140, and full-time. Yeah, and see how that also, it checks out. The total number of students in this is 200. So what's the probability someone's female? 120, right? Over 200, right? So that was not conditional. That's just a basic probability question. So that's about a 60% chance, or 0.6. So now here's the conditional part. If they're female, what's the probability that they are a full-time student? So what you do is you just look at the part if they are female. So we look at this. And so how many, what's the probability they're full-time? So how many full-time female students are there? 40. And then out of how many? Yeah, so it's out of 120, so that's where you have to be careful. So you look at the conditional part. The condition is that they are female, so you only look at that row here to answer that question. So you want full-time, so it would be 40 over 120. So that would be about 0.33 or 33%. Let's try some with cards. So you randomly select 2 cards from a deck of 52. What's probably the first card is a heart and the second is a club. First we'll start with replacing it so that one event doesn't affect the other. So this is review, so these are independent. So what's the probability the first card's a heart? Just this. How many hearts are there? 13 over 52, good. And now, since we replace it, what's the probability that the next one is a club? It's still 13 out of 52, good. So then if we just multiply those together, we'll get 0.063. Now if we don't replace the first card, so what's the probability of the first event A, which is, do we get a heart? same as before, 13 over 52, but we don't replace it. So now what's the fraction out of? There are only 51 cards, and do we still have 13 clubs, or did we already take one out? We still have a full 13 clubs, right? So it's 13 out of 51. So the denominator just decreases by 1. So it's actually a little different if we don't replace versus do. So that will be 0.064. It'll be close, but okay. A few more. They're all sort of worded differently. Suppose your area has 8 different cable companies to choose from. You and 3 friends randomly select your own cable company. What's the probability you all choose different companies? Okay, so we'll look at each event separately. The first friend can choose any company they want, right? Because no one's picked anything yet. So that's just 8 out of 8 for the first person. Doesn't matter which one you start with. But what's the probability for the second person? So we multiply. There you go. 7 out of 8. Do you see how there's only 7 if we're being unique? There are only 7 left because the first person took away the first choice. And what's the third person? There are only 6 out of 8 left to choose from. So that's how that works. So if you multiply those fractions, you get 336 over 512. I did it ahead of time because I know you can all do that. So there's about a 66% chance if you had 8 different companies and you picked at random that they would all be different. Yeah. I see. Yeah. Randomly select your own. Okay, let's fix that. So what would the next one be? 5 out of, good. And I'm just going to leave it like that because I don't have it worked out on my calendar. Thank you. And we'll figure out what that is. Thanks, Sophia. All right, example 6. Now, these get tricky, the last 2, and so I'm going to show you a new technique for doing these. It's very, I just don't know any better way, is using a tree diagram. So let's start with the last one because it's easier, okay? These can be fun and easy if you know the trick to it. So the HHS basketball team leads at halftime in 60% of the games in a season. The team wins 80% of the time when they have the halftime lead, but only 2% of the time when they don't. Only 10% of the time when they don't. Thank you. What is the probability that the team wins a particular game during the season? In other words, just in general, what's the probability that they win? So watch this. There's 2 situations. So you start by just going that there's 2 paths to take. Either the team has a halftime lead, you have to label these, or they do not have a halftime lead. That's the first condition. This is conditional probability because the events are not independent. They are dependent on each other. So it's conditional. So what is the probability they have a halftime lead? Good. So you're gonna label that branch 0.60. Right? That's what the problem said. The probability they have a halftime lead is 60%. So now by you using, process of elimination and reasoning, what does this branch have to be labeled? Yes, because either one event, remember the complement, either one event has to happen or the other. They have to add up to 1. You can't just have a missing space for nothing to happen. Okay, they have to add up to 1. Yeah. Okay, now we're good. Now we're gonna do that next. So the next decision, the next event is whether they win or lose. So we're gonna write wins or loses. So what's the probability they win if they have a halftime lead? Good. So we label that branch 80%. Because if this is true, then there's an 80% chance of that. So what do you have to label the other branch that you know? You have to label this 20%, right? So if they have a halftime lead, either they win or they lose. And now we have to have it here too, because they might not have a halftime lead. So if they don't have it, what's the probability that they win? 10%, so 0.10. And so therefore they lose is 0.9, because it has to add up to 1. It's like a decision tree. Okay, now for the final answer, once you have this tree right, it's very easy. There's 2 scenarios where they win. We're interested in what's the probability the team wins. So I'm going to put a star by those 2 cases where the teams win. And now with probability, with and, we multiply. So we just follow the tree down this branch. So 0.6 times 0.8 is the probability you get to this star. So that's 0.60 times 0.80. So that's the probability you followed that path. Or they could also win when they don't have a halftime lead. So we have to add that, because they might follow that path. So that's 40% times 10%. And this will give us our answer if we just type that in on the calculator. So if you do that, the calculator will do order of operations correctly here. You don't even need the parentheses. So you would do, the answer would be, there's a 52% chance that they win. So they have they win more than half their games during the season. So what we could conclude here. Questions on that one? We're going to do the same thing on this. We're going to make 2 decisions and practice that one more time. So on a manufacturing line, 20% of all the items produced are defective. Although all the items are inspected before they are shipped, 10% of the items are incorrectly classified as either defective or not. What percent of items will be classified as not defective? So what do you think the first branch of our tree will be? Like, what are the 2, what should I label those? Defective or not defective. So defective or not defective. This is a kind of problem that could be incredibly difficult if you don't make a tree diagram. So what do I label the defective branch? 0.2, right? Because that's what 20%. It tells me that. So what's the other branch? 0.8. 80% chance it's not defective. And then, what should we label the other part? What's the other event? It can be defective or not, and then what's the other event that's happening? It could be what or not. What's that? We don't get any probability about whether they're shipped or not. What's the other probability? Yeah. Yes, exactly. Whether they're correctly classified or incorrectly. Correctly classified, incorrectly classified. Because that's what it says. It tells us 10% of the items are incorrectly classified. Correctly or incorrectly. Okay, so what do I label this? Correctly, if they're defective, what percent are correctly classified? Yeah, 90%. Because it tells me that 10% are incorrectly classified. And the same is true here. There are also 10% of those that are incorrectly classified. So you can take that 10% and label both of those branches with the incorrectly classified. Because whether it's defective or not, the total is 10%. Because of the distributive property, it applies to both of those. So it's like using the distributive property. So this is also 90%. Okay, what are the 2 paths that we're interested in? We want to know what percent of the items will be classified as not defective. So if this is defective, but it's classified incorrectly, then does that count? Yes. So we want that situation. And what about here? If it's not defective and it's correctly classified, will that be classified as not defective? If it's not defective and it's correctly classified, will it be classified as not defective? Yes. So sometimes you have to like read it a couple times. It's kind of, there's some logic, there's a lot of language, but that's real life. There's a lot of language. Any other branches we should be starring? It's usually going to be 2 paths, but so we're ready for our final answer. So we follow this path. So what do we multiply? 0.20 times 0.10 plus? Yes. 0.90. And that will give us, if you just do that on your calculator, there is a 74% chance that items will be classified as not defective. Whether they are or not, but there's a 74%